Okay, this video is actually about something called the Larmor radius. I'm going to write that down, L-A-R-M-O-R, Larmor radius, if I'm spelling it correctly, which is no guarantee. The idea behind the Larmor radius is basically what we've looked at so far with the Lorentz force law. Let's take a look at a review question. So if we have a positive charge, and the positive charge is initially given a velocity to the right, then let's give it a number. Let's say that it's moving at 430 meters per second, and we know that the magnitude of the B field is 0.45 Tesla, and we know that the charge has a magnitude of 6 microcoulombs. Positive. Then we can actually determine both the magnitude and direction now. It's not hard for us to find. We know that the force on this thing is going to be QVB sine theta, but since we're moving at a perpendicular, sine theta again goes to 1. Don't ever forget that the sine theta is there, but in a lot of cases we're going to be moving perpendicular, so you can actually bring it to 1. So we know the force, and we can know the direction, and we can put it down as a vector. Let's go ahead and say that this is the x hat and y hat directions. And if that's x hat and y hat, that means out of the page is z hat, okay? So that is going to be z hat. Okay, so then we can put this in terms of magnitude and direction in vector quantity. So if you calculate out q times v times b, it's 1.16 times 10 to the negative 3 newtons, and we've got a magnitude. We want a direction as well. So use your right-hand rule to find the direction. We know that it's velocity to the right, magnetic field is into the page. You should get a force in the upward direction, which means that you get a positive y. Should not list that as a magnitude anymore. It is now a vector in the positive y hat direction. Okay, so here's the thing about the Larmor radius. That's only going to happen for an instant in time, because as we know, the force on an object produces an acceleration. Now, of course, the acceleration depends on the mass, and that's going to be part of this discussion. If we have a really light object, then we would expect it to go zip, okay? Because it's going to feel a very tight acceleration. Whereas the gradual force on a very heavy object, or a gradual acceleration on a very heavy object. Okay, so what happens when this thing is first moving to the right, and we know that our Lorentz force, or our right-hand rule, gives us that the direction is going to be up, and then it's going to change the direction of the velocity. Well, we have to write down a new velocity, right? Our new velocity, once this thing has moved a little bit, let's say it's moved this far, it's now going to start moving upward. So our new velocity looks like that, right? So it's going to try to move this direction. And as it does, you have to change your right-hand rule to match it, right? We now have a force that is in this direction. Well, okay. And then after it moves a little bit farther upward, it's now going to then start curving so that its velocity is that way, and then its velocity will be that way, and then its velocity will be that. So hopefully you can see the trend here is that it always has a perpendicular force to the direction of its motion, which means that it's circular motion. Now, we may remember what that is. That circular motion is centripetal force. What is a centripetal force? If any force that provides a centripetal motion is considered a centripetal force, and recall from physics 1 that mv squared over the radius is a centripetal force, right? Where v squared over r is the acceleration in the centripetal acceleration. So all we're doing is just multiplying it times m. So centripetal force here is entirely driven by our Lorentz force. So they're one and the same. Remember, a centripetal force is not a thing in its own right. It's just a description of forces that are causing something to move in a circle. In this case, it happens to be Q, V, B. Now you can always put a sine theta in there, but if you have to put a sine theta in there, then that means that you have an angle between your velocity and the magnetic field, in which case it's not actually going to move as a circle, it's actually going to move as a spiral and get closer to you, right? It's going to move in 3 dimensions in that case. If we're trapping it in 2 dimensions, it means we have to be perpendicular here, in which case sine theta is always going to be 1. So, now this Larmor effect still occurs in the case where you have a velocity that is not in plane, but it's easier to analyze from this point of view. So we get then mv squared over r is equal to qvb. But we have a v on both sides. We have one v here and two of them here, so let's cancel that, and we get an equation that is quite useful for us. We can actually solve for r, and if you run your algebra correctly, then you should get this. This is the Larmor radius. In other words, that is the radius of the circle that a charge traverses in a magnetic field, the Larmor radius. Notice that the upstairs term here is a momentum term. So basically, the more momentum this charge has, the harder it is to steer it in a circle, which is what we were talking about before. So if I have a bowling ball with a certain charge that's moving very fast, it's really not going to be very affected by this. Instead, if I have like a piece of styrofoam that's moving very slowly, it is more easily going to be affected by this. If either the styrofoam or the bowling ball has a significant charge on it, that's going to affect it more. So the larger the charge and the larger the B field, the more influence the magnetic field can wrestle control over that moving charge. And therefore, both of them together will form a certain radius. Okay, that's Larmor radius. It's pretty straightforward. Just remember, this is on your equation sheet. This is what it represents. But even if you can't remember this or can't find it on the equation sheet, it's not actually that hard to derive on your own. But you'd have to remember the centripetal force equation to derive it on your own. So locate it on your equation sheet and make sure you're aware of what that R means. So in the next video, we're going to actually describe the Lorentz force on, instead of a single charge, on many charges that are actually going through a conducting wire.